Okay, ladies and gentlemen, here's video 2, and obviously video 2 is on intermolecular forces. So we're going to be talking about now, instead of the forces inside the molecule that are affecting the atoms as they go together, we're going to be talking about the forces that affect molecules outside. So how do molecules interact together? We're mostly going to focus on covalent bonds, but ionic bonds are the strongest. So we're going to see three intermolecular forces, but there's an ion-ion dipole that's actually stronger than all of these. So I just want you to be aware that we're going to focus more on covalent bonds because they're the ones that we see more intermolecular forces in, because remember we talked about the fact that ionic bonds are always affected by the electrostatic charge. And so when you have ions, multiple ions together, they're going to line up so that positive ions aren't together and negative ions aren't together. So please make sure that you're aware of that, that even though we're kind of glossing over that and we talked about it earlier, we're not forgetting it, but we know that that's a really strong thing. So we're just kind of moving on from there and talking about the things that we don't have a great understanding of. So here we go. So intermolecular forces. First, an interstate highway runs between different states, like I-75. I-75 runs between Michigan all the way through to Florida. So Michigan, Ohio, Kentucky, Tennessee, Georgia, into Florida. And you can get to all of those states by traveling on Interstate 75. And it's kind of interesting, and it's a beautiful travel. So if you've never done it, I suggest you do. Well, that means that an intermolecular bond is an attraction between different molecules. So if we're talking about one molecule and another molecule and how they're interacting together, not the atoms interacting with one another and the bond between them, but the interaction of molecule to molecule and how that's going to happen. So the intermolecular forces are attractive forces between molecules. Intramolecular forces hold atoms together. So inter versus intramolecular. Well, 41 kilojoules to vaporize 1 mole of water is an intermolecular force, because we're talking about how do we get those water molecules that are next to each other to want to become gases. So we have to break the forces that are holding them together to get it to be a gas. Whereas if it takes 390 kilojoules to break all of the bonds between O and H in water, that's intramolecular, because we're talking about the O and the H bond inside the molecule. So I want to give you this idea. Vaporization and things like that, those things that are changing state, are all talking about intermolecular forces. So generally, intermolecular forces are much weaker than intramolecular forces. So you can see it only takes 41 kilojoules to vaporize 1 mole of water, but it takes 932 kilojoules to break all of the OH bonds in water. So that's pretty interesting. You can see the greatest difference here. See how low this number is and how high that number is. And you can see this general statement here about generally intermolecular forces are weaker than intra is absolutely true. So here are some intermolecular forces, things that we will talk about. Boiling point, we will talk about that. Melting point, also, that makes complete sense. So if we want to get something to boil or melt, we have to overcome the interactive forces between the molecules to get them to move from one phase to another. So that makes sense. Now, heat of vaporization is exactly what we were talking about in that first bullet point, the 41 kilograms. That's the amount of energy it takes through the amount of heat it takes to go from a liquid to a gas. Heat of fusion is the amount of energy it takes to go from a liquid to a solid. And heat of sublimation, this is kind of a different one, and we only know of one substance that we've seen that it happens to is dry ice. Dry ice is carbon dioxide in solid form, and so we want to know how much heat has to be applied to take it from solid form to gaseous form, because we know dry ice turns directly into a gas. It does not go into its liquid phase. So all of these are measures. These are ways that we can quantify intermolecular force inside the atom. So we've got the quantities. Now we want to go to some of the qualities. How can we determine that? So there are 3 different types of intermolecular forces. Now remember, this is not including the forces that we just talked about with the ionic compounds, the ion-ion interaction. Sorry. So the bond type is hydrogen. Hydrogen bonding. Now it's called bond type, but I want to say force type more than bond type. So let's Let's cross that out and say force type. Force type. And let's say force strength. Because I really don't want to talk about these as bonds. I think that's what confuses a lot of people, because people talk about them as bonds. And I got to be honest with you, this one is actually known as hydrogen bonding. And it's really not a bonding. But you can see it's pretty strong. But there's a reason it's pretty strong, and we'll talk about that in just a minute. The second one is a dipole-dipole. And this is between polar molecules, and we'll explain a little bit more, because hydrogen bonding is actually a specialized type of dipole. But you can see the strength is about medium. So anything that's polar has some pretty good interactions. Okay? And then finally, London dispersion forces. London dispersion forces are very weak. They're also known as van der Waals forces. That's the old name for them. But London dispersion forces are basically interactions between nonpolar molecules that behave sort of like this dipole and hydrogen bonding, and there's still an interaction, but you can see those interactions are quite weak because there's nothing really holding them together. So here we go. Hydrogen bonds. These bonds may occur between polar molecules. They do actually occur between polar molecules, but only special polar molecules. It has to be hydrogen directly bonded to one of three elements: fluorine, oxygen, or nitrogen. If it is not bonded to fluorine, oxygen, or nitrogen, it is not considered a hydrogen bond. The reason this is because these are the three most electronegative elements on the periodic table. And so we get this much greater difference in electronegativity. So the electronegativity difference of all three of these is somewhere on the scale of 1.2 to 1.9, the electronegativity difference. So these are super, super polar. And so because of that, we get a stronger interaction between these molecules because they're going to line up with the slightly negative poles facing the slightly positive poles. And that interaction is going to behave sort of like our electrostatic interaction. But since it's not really ionic, it's not completely like that. So I know we're splitting hairs, and I know that gets confusing. So if we look at the water molecule here, we can see that we have this water molecule right here, and you can see the slightly negative charge here and the slightly positive charges here. And then you can see this second water molecule here. We'll notice that the slightly negative charge is lining up with the slightly positive charge. And this is the hydrogen bond. This dotted line represents the hydrogen bond. It's not really a bond. It's more of an interaction. So they draw a dotted line, but it's not like this guy right here. This guy contains a lot of energy. There's a lot of stored energy right there in that particular one. Right here, there's just a little stored energy. Okay? It's the amount of energy that it's going to take to get those two molecules further and further away from each other. And so you just have to remember that this is really not a bond, but it behaves sort of like a bond. Okay? It only happens when it's fluorine, oxygen, or nitrogen that the hydrogen is directly attached to, though. So we have to remember that. The next one is dipole-dipole bonds. Now this is a whole lot like hydrogen bonding. The difference is that you can have any polar covalent molecule. So it can be from the 0.5 all the way up. If it is not bonded to fluorine, oxygen, or nitrogen, then we see a dipole-dipole bond. And you're going to see there's an attraction between the positive end and the negative end, just like there was in hydrogen bonding. The difference is this is not oxygen, this is not fluorine, oxygen, or nitrogen. And this may not be hydrogen. Okay, this looks a whole lot like a water molecule, but what we're trying to show you here is that these things are not what we looked at before. So this is any polar covalent compound. So any compound that has a difference of between 0.5 and 1.2-ish, okay? So we're talking about the slightly polar covalent compounds here. And they are going to have a slightly positive end and a slightly negative end as well. And you see they kind of flipped it around so that the two end would be a slightly negative. But you can see the interaction is still here. There is the dipole. There is the dipole bond. There's the dipole force right there. And so this interaction, it is a medium strength interaction. It is not the strongest. Hydrogen bonding is the strongest intermolecular force in a covalent bond. Dipoles are the next strongest when we're talking about covalent bonds. But remember, they're behaving sort of electrostatically. So, you know, you can kind of see why it might work. So the next one, the last one, sorry, Oh, this isn't working. So why is the hydrogen bond considered a special dipole interaction? Well, if you can see here, these three circled substances are water, hydrofluoric acid, and ammonia. So hydrogen bonded to nitrogen, hydrogen bonded to fluorine, and hydrogen bonded to oxygen. Look at the boiling points. Remember we talked about boiling point being a measurement of intermolecular force? Well, if you look at these boiling points, these three compounds have the higher boiling points of almost anything. We've got a few things over here that are higher than ammonia, but if you look in the same group, there is not much that's higher, okay? Not much that's higher over in here. So we can see very clearly that this hydrogen bonding is just a really special dipole interaction, and because they're so different in electronegativity, we see that that's happening. So London dispersion forces, aka van der Waals forces. These bonds occur between nonpolar molecules. They're represented by black dashes between molecules. The dispersion forces usually increase with increasing mass. So the more massive a substance is, the more dispersion forces that something might have. So if we look over here, we see methane gas. Methane is a completely nonpolar molecule. Even though there's a difference between hydrogen and carbon, because they're pulling in opposite directions, up and down and side to side, there is no pole being formed here. So we have these really strong bonds right here that it's showing right there. It's trying to show this bond or this bond right here between the particles in the actual molecule, the hydrogen and carbon. But these are the London dispersion forces that we're seeing right here. They are very weak. And as we said, they increase with increasing mass. So that's going to help us a little bit later. So what type of intermolecular forces exist between each of the following molecules? We have these three molecules. So HBr. Well, we know H and Br are going to have a pretty good electronegativity difference, a 1.2 and probably somewhere on the order of 3.0, 2.9. So we're going to have a pretty great difference. So we know that HBr is polar. So there's going to be a dipole force because it's not hydrogen, nitrogen, or fluorine. It's going to be a dipole force, not a hydrogen bonding. And there are also some dispersion forces between there. Pretty much there are dispersion forces between anything, but the greater one is the dipole force. So then we get methane. Methane is nonpolar, so the only intermolecular force they have are dispersion forces. Now we have this sulfur dioxide. This is a molecule of sulfur dioxide. Notice the bent structure. That means that the electronegativity difference between these two is probably greater than 0.5, and since they are not opposite one another, that also means that there's a dipole. There is a little bit of a polar nature going up inside of the S here. So, or maybe it's going down toward the oxygen, because the oxygens are probably greater in electronegativity. So we have a slightly negative charge right here and a slightly positive charge right here. So because we have a polar molecule, we have dipole-dipole forces, and there are also dispersion forces between that. So what do you know? What type of intermolecular bond exists between each molecule? So H2. Well, H2 is nonpolar. So because it's nonpolar, there must be something else. I'm sorry. Let me look at these guys first. Okay, so here we have H2, NH3, HCl, H2O, C2H6, and Ni3. So let's look at them separately. So here we go. H2 has London dispersion forces. NH3, hydrogen bonding. It's nitrogen. So hydrogen hooked to nitrogen, hydrogen bonding. HCl, dipole-dipole, is the strongest. Okay, H2O, hydrogen bonding, hydrogen hooked to oxygen, hydrogen bonding. C2H6, it is nonpolar, so it is going to be a London. And Ni3 is going to be dipole-dipole. It's not a hydrogen bond, but it is still polar. So we're going to go ahead and stop there. I'll probably put another video up tomorrow, a little bit more on some interactions and some properties that we're going to be talking about tomorrow in our lab. So thank you very much. I hope you enjoyed.